A very good day to Dr. Chong. The group consists of Brian Lai, myself, Dixon Teo, and Yo Yi Liang. This presentation will discuss the bicycle frame for track cycling. The presentation consists of background and application, key performance requirement, material comparison, final material selection, sustainability and socio-economic consideration, and finally, conclusion. The bicycle frame is the main structural component, which connected the handlebar, saddle, pedal, and wheels. Therefore, it can determine the overall geometry, stability, and rider performance. Most of the bicycle frame use diamond-shaped geometry for strength and load distribution because it must withstand dynamic stress, vibration, and impact during racing. The speed of the bicycle can go up to 80 kilometers per hour in sprint event, so the design is crucial. The first bicycle is called the Swift Walker, which is used a wooden frame. The transitional materials are steel and aluminum alloy, valued for strength and manufacturability. In modern, frames are using carbon fiber reinforced polymer. The application used in Olympic track cycling event is lightweight. Lightweight can bring acceleration, climbing efficiency, and increase overall speed. Regarding bicycle design, stiff frames can improve power transfer, maximizing cyclist performance, and aerodynamic tube reduce air resistance, which can increase the bicycle speeds. So, moving into the key performance required. A high strength to weight ratio, the frame must resist high pedaling load while remaining very light for speed and acceleration. Having a high stiffness can minimizing frame flex to improve power transfer and responsiveness, especially during sprint. Having a good fatigue resistance is essential to withstand millions of loading cycles during training and competition without cracking. Material and shape must be manufactured to allow efficient tube forming or joining to achieve precise geometry and equal quality. Aerodynamic frame is efficient, allowing to minimizing drag to allow higher speed with less energy while in sprinting and time trial event. And that's all from me. I will pass to Dixon.
Thank you, Brian. After identifying the key performance requirements, let's compare two cadet materials for bicycle frame, which are 6061T6 aluminum alloy and T700S carbon fiber reinforced epoxy composite. Starting with strength to weight ratio, the aluminum alloy has a density of 2.7 gram per cubic centimeter and a tensile strength of about 370 megapascal. CFRE, on the other hand, is much lighter at 1.8 gram per cubic centimeter and have a higher strength with a tensile strength of 2,860 megapascal along the fiber direction. This difference means CFRE offers a far superior strength to weight ratio, which is critical for Olympic track cycling. A light frame accelerates faster, improves climbing efficiency, and reduces rider fatigue over long races. In fact, CFRE frames can be up to 40 to 45% lighter than aluminum alloy for the same volume, giving athletes a real competitive edge. Aluminium Young modulus is around 68.9 gigapascal, while CFRE reaches 134 gigapascal longitudinally, which is almost double. Higher stiffness means less frame flex, so more pedaling energy is converted into forward motion instead of being lost to deformation. This improves power transfer and responsiveness during sprints. CFRE also allows directional stiffness tuning through fiber orientation, which aluminum cannot achieve. Engineers can design frames that are stiff in bottom bracket for efficient power transfer while keeping the seat stay slightly compliant for comfort. This level of customization is major advantage for performance optimization. Fatigue resistance is another key factor. Aluminium typically has a fatigue limit of about 97 megapascal, whereas CFRE can withstand up to 400 to 800 megapascal under cyclic loads. This translates to a much longer lifespan under extreme racing conditions. CFRE's composite structure resists crack propagation better than metals, reducing the risk of sudden failure. For elite athletes who train and compete at high intensity, its durability ensures consistent performance and safety. It also means fewer frame replacements over time, which offsets some of the initial costs. However, manufacturability and cost presents trade-offs. Aluminium frames are easier and cheaper to produce, and it is only around 2,899 ringgit per frame by using well-established welding and machining process. CFRE frames cost roughly 9,977 ringgit and require complex layup, resin infusion, and autoclave curing. Repairability is also a challenge. Aluminium can be welded, while CFRE often needs specialized repair techniques and sometimes full replacement. Production rates are also slower for CFRE, making it less accessible for mass market bikes. However, for Olympic level performance, these trade-offs are often justified by the performance gains. Finally, aerodynamics. Aluminium frames are limited to simpler tube shapes and weld joints which can disturb airflow. CFRE allows seamless molecule construction and complex aerofoil profiles, which reducing drag and improving speed, which are critical for Olympic track cycling. Next, I will pass the time to Yi Liang.
Thank you very much, Dixon. Next, we're moving on with the final material that we selected. So throughout the comparison, we've selected T700S carbon fiber reinforced epoxy, CFRE, as our material to make our Olympic bicycle. So let's talk about the benefits. So its higher strength to weight ratio compared to aluminium, which is around 40 to 45% lighter than aluminium. And also the tensile strength is 2,860 megapascal, which is greater than aluminium's 370 megapascal. So the greater the tensile strength, the better the material is. So moving on with higher stiffness of carbon fiber reinforced epoxy, it has a Young modulus of 134 gigapascal, and the specific stiffness of CFRE is around 74.4 gigapascal cubic centimeter per gram, which is 3 times better than aluminium. And next is the higher fatigue resistance, which have a fatigue limit of around 400 to 800 megapascal, and it's really outstanding compared to aluminium. And lastly, we have the aerodynamic and design. So CFRE enables workers to build a more complex and aerodynamic shapes for bicycle frames. And due to its lightweight, it's ideal for high-speed performance. However, there's a trade-off, which is that its costs higher compared to aluminium and it's complex to manufacture and repair. Moving on with the sustainability and social economics consideration. So let's talk about long-term sustainability consideration first. So it has been separated into two parts, which is the carbon footprint part and the end life management and recycling challenges. So for the carbon footprint, it requires a high energy intensive while manufacturing. So it requires around 100 to 150 megajoule per kilogram of energy, which emits around 10 to 20 kilograms carbon dioxide per kilogram of fiber, which cause a higher impact compared to aluminium alloy. And next, let's talk about the end life management and recycling challenges. So CFRE uses epoxy that cannot be remelted. This makes the recycling process to become very complex. And current disposal way is that 90% of end-of-life carbon fiber sport equipment has ended up in landfill. So however, there's several recycling methods for CFRE, which are pyrolysis and solvolysis. However, it's really costly and also it requires large energy to recycle. Moving on with the socio-economic consideration. So let's talk about the cost and accessibility. So for the cost, the CFRE frames cost around 2,500 to 500 USD, which is United States dollar. And this causes it to limit access to only elite athlete as they have sponsor or even like they have the support from the national team. And moving on with the growing demand, despite sustainability concern,
So the use of CFRE has been growing around 25% greater, which means that more and more people are access to CFRE frame. And in the future, the recycling initiative could have create several opportunities, which are to create jobs and also reducing costs. And that's all from me. I'll pass it back to Brian.
Thank you, Yi-Liang. I'm Brian. So in conclusion, carbon fiber reinforced epoxy, CFRE, is the optimal materials. It has a superior strength to weight ratio, which is lighter and stronger than aluminium, high stiffness to efficient power transfer and improved handling, excellent fatigue resistance, which has a longer lifespan under extreme racing conditions, and enable aerodynamic and complex design for maximum speed. However, it requires a higher cost and complex manufacturing, but it was justified by performance benefit in the future. Sustainability challenge remain, and recycling innovation could improve environmental impact and accessibility. And this is our list of reference. And that's all from us. Thank you.